Okay, so now we kind of have a basic idea of what a matrix is, how to define it, and how to do row operations on it to solve a system of equations. Now we want to start working with the matrices themselves, and start doing operations on the matrices different than just row operations to solve a system of equations. And in order to do that, we kind of need to make sure we understand all the properties of them. So first off, really quickly, just to review if we don't remember it from before. Suppose I have one matrix like this. We'll just make them easy. 1, 2, 3, 4. Over here I'll do 1, 2. Here I'll do 1, 2. And this is 3, 1, 2, 4, 1, 7. So I have a bunch of different matrices there. First, I care about the size of the matrix. The way we write the size of the matrix, the order of the matrix, is by the number of rows and the number of columns. So in this case, this one has 2 rows and 2 columns. So it's 2 rows by 2 columns. Rows first, then columns. Here, this has 1 row and 2 columns. So it's 1 by 2. This has 2 rows and 1 column. So it's 2 by 1. And then this one right here, 2 rows, 3 columns, so it's 2 by 3. And again, we can have any type of combination of rows and columns that we want. All you do is count out the rows, count out the columns. That determines the size of your matrix. 2 by 2, 1 by 2, whatever. As far as terminology goes, we do have a little bit of special terminology. If the number of rows and the number of columns are the same, that's called a square matrix. We've actually used that before. So that would be a square matrix. None of these other ones are, because the rows and columns are different. If you end up with something like this, where you have 1 row and multiple columns, this is actually called a row matrix. Or a lot of times it's called a row vector, because it's really the same as a vector now. Same idea here, where you have multiple rows and 1 column. This is called a column matrix, or a column vector. Same idea. So just a little bit of terminology, but we need to know that in order to kind of mess around with what we want to mess around with as far as operations go. First off, we care about equality. And for matrix equality, matrix A equals matrix B if and only if A and B are the same size and Aij equals Bij for all I and j. So essentially, equality means exactly what we think it would mean. 2 matrices are equal if they are identical, if they're the exact same size, and if every entry, A sub ij, row column, equals B sub ij, row column. So in this case, none of these matrices are actually equal. And one thing to be aware of, clearly these are all different, but right here, this is 1, 2, this is 1, 2. They have the same entries, and I mean, let's face it, this is 1 row, this is 1 column. They're kind of sort of the same. They have more or less the same stuff in them, but they are not equal, because this is 1 by 2 and this is 2 by 1. And they can only be equal if they're the same size. These are not. There's actually another relationship that those two things have that we'll explore later on. Because again, they're kind of the same, with kind of the same stuff in them, but they're not equal, but there's something else that's not exactly equal. But we'll deal with that for later on. So for right now, 2 things are equal if they're identical, if everything is the exact same. But once we have the idea of equality, well, Working with matrices is no different than working with integers or rational numbers or irrational numbers. Once you define them, once you define an integer, once you define a rational number, once you define a matrix, then you have to define the operations on those numbers, those things. How do you add integers? How do you add rational numbers? How do you add complex numbers? How do you add matrices? How do you subtract matrices? Can you multiply matrices? So we want to run through all of those operations. And as far as it goes, for addition and subtraction, let's see, A and B must be the same size. So you can only add and subtract matrices that are the same size. So if we have A equal to 1, 2, 3, 4, we'll let B equal 0, 2, 4, 1. Suppose you want to add them. A plus B. I would argue the logical way to think about this is, well, if I'm going to add this to this, if I'm going to add two square matrices that are 2 by 2, then I should get a 2 by 2 matrix out, which is exactly what we get, and we add in the way that seems logical. You add component-wise, just like you would do with vectors, just like you would do with a lot of things. So in this case, 1 plus 0 is 1, 2 plus 2 is 4, 3 plus 4 is 7, 4 plus 1 is 5, and there's my sum. If I wanted to subtract them, A minus B, well, I would logically do the same thing. I would take my 2 by 2 and my 2 by 2, and I would get a 2 by 2 out, and I would subtract component-wise. 1 minus 0 is 1, 2 minus 2 is 0, 3 minus 4 is negative 1, 4 minus 1 is 3. And there's my subtraction. And one thing I will point out now, and you will see it as you start doing your homework that I assigned for this week, you're going to do a lot of calculational work with these matrices like this. It's easy, it just lets you kind of practice the basics, make sure you understand how to do the operations on them. But then there's also the understanding of what this addition means and how we define it and how to define it and prove different things algebraically. So maybe, and again, I gave you some proofs for homework. They are not really all that challenging. Later in this video, I might kind of pull one out of the air and work through it. But I just want you to get the feel for how to prove these things out. And it works pretty well with these basic operations now because the proofs themselves are pretty straightforward because the operations are straightforward. One little tip maybe that I'll give you. If you are trying to prove something for matrices in general, for the sake of argument, say you were defining addition, you would not define it on a 2 by 2 or on a 3 by 3 or on anything like that. You would use the most general form of a matrix that you could think of. So maybe let A equal the matrix A11, 1n, AM1, AMN. So there's my m rows by n columns, my m by n matrix. Do the same thing for B. That would be B11 out to B1n, BM1 over to BMN. There's my m by n matrix for B. Now if I wanted to define addition, I would say A plus B is equal to A11 plus B11 over to A1n plus B1n, AM1 over to I left off the B term, plus BM1 and AMN plus BMN. And now we have the actual algebraic definition of matrix addition. They have to be the same size, you add component-wise. The reason I mention this, and from a math perspective, the reason we define it this way and want to be able to write it out this way is because now I can actually use all my properties of real numbers. The matrix is this different thing. It's this rectangular array of numbers. But now inside here, each individual entry is just a real number, real number. I can add real numbers. Now this is a real number. So I can do all of the operations on real numbers that I know component-wise. Those of you who took Calc 3, a lot of times when we were proving things with vectors and vector functions, we did the same thing. You define a vector operation in such a way that you can work with the real components of the vector, because then you can apply all the operations on the real numbers that you know. And again, this is really straightforward, but when you're told to prove something, if you're told to prove something that involves matrix addition, define your matrices this way, use this definition of addition, and then go from there. Work with the real numbers. I'm kind of thinking, if it helps, and you'll see this with your homework, what about commutativity? In real numbers, addition is commutative. 2 plus 1 is the same as 1 plus 2. Would matrix addition be commutative? Well, that's A plus B right here. If I defined B plus A, I'm only going to do like one entry here. If I defined B plus A, that would be B11 plus A11, and I'll leave the rest off. Because now, the first entry here is A11 plus B11. The first entry here is A11 plus B11. Those are real numbers. Those are the same, because addition is commutative for real numbers. So now I can say, again, I would have to write it out formally here. I'm just kind of shortcutting this. But now I can say that A plus B in matrices form is equal to B plus A. So matrix addition is commutative. These are the types of proofs you're going to be working with on your homework. Write out the matrices, regular m by n matrices in general. Apply the operations as we define them, and then look at the components and see what you get, and manipulate those. Good. So that's addition and subtraction. But wait, there's more. Because there's also multiplication. We're not going to worry about division. But as far as multiplication goes, there are actually two different types of multiplication. First off, there's what's called scalar multiplication. And the way scalar multiplication works is, we'll say C times A. Scalar C times matrix A is equal to, well, let's see, right over here, we'll say A is equal to the matrix A11, our standard A1n, AM1, AMN. So I have my standard m by n matrix. CA would be CA11, CAM1n, CAM1, CAMN. So if I do scalar multiplication, a scalar times a matrix, I just distribute the scalar in and multiply it by every component of the matrix. So if I have, let's see, A is equal to 1, 2, 0, 7. If I want 3A, I multiply the 3 by each component. I get 3, 6, 0, 21. And again, this multiplication is similar to the multiplication that we're used to. We actually use it with vectors when you multiply a scalar times a vector. And all you do is multiply the scalar by each component. But that makes sense because, well, suppose my matrix B was a row matrix, which would be a row vector, 1, 2. That's just a vector. I mean, I'm calling it a matrix, but I could just as easily do this. If I had 2b using the vector, I would get 2, 4. So it's only logical if I have 2b up here, I should get 2, 4, the exact same. Just distribute the 2 in. And again, the idea here is everything you have done with vectors, vectors are really just kind of a special case, the row vector or column vector of a more general idea involving matrices, which don't have to be just rows or columns. They can be a big rectangular array. But the principles still work the same. So we have addition and subtraction. We have scalar multiplication. Well, if these were vectors, once you define the scalar product of a vector, scalar times a vector gives a vector, then you start talking about dot product. And if you all remember dot product, and if you have not done dot products, it does not matter. But if I have a dot product really quickly for vectors, suppose A is 1, 2, and B is equal to 2, 4. A dot B, we multiply component-wise. 1 times 2 is 2, and add. 2 times 4 is 8, and I get 10. And now the question is there kind of an equivalent idea of vector multiplication? I'm sorry, not vector multiplication, dot product, matrix multiplication. We have scalar multiplication, scalar times matrix. Can I kind of generalize this? Vector times vector? Can I do matrix times matrix? I'm actually going to leave this here deliberately. And as it turns out, you can. But it's a little bit different. And I'm actually going to write this out, rather than writing it out algebraically long form, I'm just going to do an example of this so it's easier to see. And the idea is, suppose I have a matrix. 2, 1, 3, 1. That's a 2 by 2. And I'm going to multiply it by the matrix 2, 1, 1, 1, 0, 4. That's 2 rows by 3 columns. And deliberately on my part, those are different sizes. For addition and subtraction, you cannot add or subtract them unless they're the same size. Matrix multiplication is different. There's a trick. In order to multiply them, if I call this A and this B, I want to find A times B. But you can only do it if you meet one requirement. You have to look at the 2 middle terms right here and see if they're the same. If they are the same, the matrices can be multiplied. If they can be multiplied, then you look at the 2 outer numbers, and that tells you the dimensions of the matrix you will get. Meaning, 2 by 2, I'm sorry, this is the 2 and this is the 2, they're equal, so they can be multiplied. My answer will be a 2 by 3. So I should get something with 2 rows and 3 columns. And here I'll just arbitrarily call this x, I don't know what it is, x11, x12, x13, x21, x22, and x23. And I need to find all of those entries. But one of the reasons we write all these subscripts here to keep things organized is because it also helps us understand where all of our information comes from. In this case, when I multiply these, this is the x11 term. How I actually get it is by taking the first row of the first matrix and multiplying it by the first column of the second matrix. And then I essentially apply my dot product idea over here. I do, instead of vector times vector component wise and add, I do row by column component wise and add. So here, I will do first row, first column. 2 times 2 is 4, 1 times 1 is 1, 4 plus 1 is 5. Here, this is first row, second column. So I do first row, second column. 2 times 1 is 2, 1 times 1 is 1, 2 plus 1 is 3. First row, third column, first row, third column. 2 times 0 is 0, 1 times 4 is 4. Now here, second row, first column, second row, first column. 3 times 2 is 6, 1 times 1 is 1, 6 plus 1 is 7. Second row, second column. 3 times 1 is 3, 1 times 1 is 1, 3 plus 1 is 4. Second row, third column. 3 times 0 is 0, 1 times 4 is 4. And there's my product. So again, understanding these subscripts will actually help you a lot because this tells you where your answer comes from. That being said, the multiplication is really just straightforward. Multiply a bunch of numbers and add them together. As long as you remember where each entry comes from, you're good. The devil here is kind of in the details and understanding what's going on, meaning remembering that I have to check the dimensions of my matrices and make sure this holds. These two inner numbers have to be the same. The outer numbers are the dimensions of my solution. But we were talking about properties of numbers and operations and all that, commutativity and things like that. What is B times A? Well, in this case, B is a 2 by 3, A is a 2 by 2. Now, I can't even multiply those. Which means A times B is not the same as B times A. B times A doesn't even exist because the dimensions are different. Which means matrix multiplication is not commutative. It's not even defined in some instances based on the dimensions here. You could ask yourself if you wanted to kind of specify it even more. What if A is n by n and B is n by n? So suppose they're square matrices, 1 by 1, 2 by 2, 3 by 3, whatever. Then the matrix multiplication would be defined. Is it commutative? There's different ways to go. You could try to prove it is commutative algebraically, define 2 n by n matrices, multiply using our rules and see what you get. Or you could try to look for a counterexample. I would suggest looking for a counterexample. I'm not going to do it, but just pick an n by n matrix, a 2 by 2. 1, 2, 3, 4. Pick another one. 3, 7, 0, 6. Who knows? Just make it up. Multiply those out. If this is A and this is B, see what A times B is, see what B times A is, see if they're the same. They won't be. But again, it's just one of those little things that pop up with matrices. All the other operations that we think of when we think about multiplication and addition are commutative with other types of numbers. With matrices, it's not. They're non-commutative. The last thing I will point out, I'm going to make another video, but the last thing, just because we mentioned it here, clearly this matrix multiplication idea is the same idea that we use for vectors. And vectors are really just special cases of matrices. But can I apply my multiplication for matrices to the vectors? Because vectors are matrices, the column and row matrices. But, well, if I define A as 1, 2, don't put the column, and B, now I have to write them as a matrix, so I'll make these capital, and B as 2, 4, what's A times B? Well, the problem is, this is 1 row by 2 columns. This is 1 row by 2 columns. And those are not the same, which means I can't multiply them. So I have a problem. But there is actually a trick here, which we kind of sort of mentioned at the beginning of this lecture. We have row matrices, row vectors. We also have column matrices and column vectors. The trick here is, write B instead of as a row vector, write it as a column vector. Now, this is 2 rows by 1 column. Now the middle numbers are the same. And keep in mind, with these middle numbers being the same, I can multiply them. My solution will be the outside, which is 1 by 1, which is just a scalar. It's a 1 by 1 matrix, which is a scalar, which is exactly what this says I should get. Now I multiply row by column. 1 times 2 is 2. 2 times 4 is 8. 2 plus 8 is 10. And again, the idea here being, these vectors are just special cases of the matrices. They are matrices. They're row and column matrices. We have to manipulate them a little bit to get the operation to work the way we want for all matrices. But we also said at the beginning that, say in the case of B, 2 and 4 and 2 and 4 are not the same. The dimensions are different. 1 is 1 by 2 and 1 is 2 by 1. So they are not equal, but there is clearly a relationship there. Because if I just take this and flip it from horizontal to vertical, if you will, it allows me to perform the operations I want and get the answers that I know I should get. Like I said, those are more properties of matrices that we'll see later on. We're going to leave them off for right now. I'm going to stop this video now simply because it's really long, but I'm going to make another one going over some more properties and how we can apply this to problem solving.